Good afternoon, everyone. I'm Kishan S. Atre. I'm a graduate student under Dr. Shah. Today, I'll be giving a brief tutorial on Keras. So let's get started. So there are several deep learning packages. The popular ones are TensorFlow, PyTorch, Keras, Chainer, Caffe, CNTK by different people. Among this, Keras is one of the easiest to learn, and it's easy to prototype too. So I'll just give you the overall overview of this tutorial. So I'll be talking about what is Keras, basics of Keras environment, building convolution networks. I'll teach you how to build recurrent networks, and I'll also introduce some other types of layers and loss functions and optimizers available in Keras, and also how to use pre-trained models in Keras, and saving and loading weights, as well as just a brief overview of popular architectures in deep learning. So what is Keras? So Keras is basically a deep network library written in Python, and it's a high-level neural network API. It's modular, so building model is just stacking few layers and building the computational graph. It runs on either TensorFlow, Theano, or CNTK. You might be wondering why use Keras when you have so many frameworks. So there are several advantages to it. One is that you can do a very fast prototyping. You just ignore the details of implementing backprop, computing gradients, or weight updating. So you don't have to worry about any of those. All you have to do is just design the model and prepare the data and run it. It supports convolution, recurrent layers, and combination of both. It runs seamlessly on CPU and GPU. That's very useful, and almost any architecture can be designed using this framework. The biggest plus point is it's open source, and there's a large community support for Keras. So the working principle behind Keras is something called as a computational graph. This is what even Theano and TensorFlow uses. Since Keras is built on top of it, this utilizes this framework. So computational graph is as shown in the figure on the right. So let's say we want to evaluate a complex expression, and this complex expression can be sort of broken down into simpler expressions. So basically, neural networks are function approximators, and they basically are a very complex function and an expression. But if you want to implement that on the computer, then you want to break the entire complex expression into simpler expressions, and then implement each of those separately. So the advantage of computational graph is that you basically break down the complex expression into simple ones, and then it's useful for calculating derivatives using backpropagation. So here's an example where this graph is currently computing E equals C star D, and then C is dependent on A and B, and D is dependent on B, where A and B are inputs. So if you give A and B as 2 and 1, then it calculates each of these small expressions, and then it computes the output at this point. Now you can sort of think of this as a neural network, where each node here in the blue is a layer, and each layer is doing a computation. It's computing some expression. So if you want to compute gradients with respect to each other, with respect to the variables, then we can see an example here where if you want to compute the partial derivative with respect to C of E, then we have the final value E equals 6, and then delta E by delta C, you get it as 2, because you already have the value of D that's coming in here, and then you just do a simple math and you get 2 here. And the same thing can be repeated throughout the computational graph. The other advantage of this is that it's very easy to implement in the distributed computation. This is what is being leveraged by GPUs. And all you have to do is just specify the inputs and the outputs and make sure that the graph is connected. So this is something that's being utilized by TensorFlow, Keras, and Theano. So everything happens in the backend, so you don't have to worry about computing any of these. So the general pipeline of implementing any artificial neural network is as follows. We design and define the neural network architecture depending on what application that we want to use it on. and we select the optimizer to perform the optimization. Mostly it will be gradient descent. There are a few cases where we do gradient ascent. And selecting the optimizer is a crucial aspect. And we need to specify the loss function. So the ultimate aim of neural network is to minimize the loss function, and selecting that loss function makes a lot of difference. And we start training it. And then we need to select an appropriate evaluation metric and evaluate our model at the end using the test set. So we'll look at the major steps that we need to implement in Keras to run any neural network. So there are 5 major steps. One is preparation of the input. You specify the input dimensions, you do pre-processing, ZCA whitening, and there are so many other pre-processing steps. You do all that, prepare your labels, and then you define the model architecture, and then you define the model architecture and build the computational graph. So the architecture that you decide depends on the problem that you are tackling. And you specify the optimizer and configure the learning process. So optimizers, there are several optimizers available, and each have its own advantages and disadvantages. And then you explicitly specify what are the inputs to your computational graph, what are the outputs, and then what loss function do you want to minimize. The final step is to train and test the model and evaluate it. So one of the key advantages is that the gradients, or the backpropagation gradients, are calculated through auto differentiation, and parameter updates are done automatically in the backend. So you don't have to write any code to do that. So let's look at a procedure to implement neural networks. So in Keras, Keras is basically divided into 2 classes. One is called sequential class, the other one is functional class. In sequential class, so basically I'll explain these two in the future slides, but let's look at how Keras code looks like in a sequential class. So the first step is to import something called a sequential class from keras.models. And then sequential is it's a class, you assign it to an object, and you just start stacking layers by using add method. So here we're looking at 2 layers, dense layers. So dense refers to the fully connected layers, which is same as multi-layer perceptron. A fully connected layer with 64 units. 64 units here refers to the number of nodes in that layer. And since this is the first layer, you have to specify the input dimension. So let's say we have prepared input, and the dimension of the input is a 100-dimension vector, and you feed that into the dense network, dense layer here.
So 64 is like a neuron.
Yeah. So there are 64 neurons, and each of those neurons are connected to these 100 inputs, 100-dimension vector. Right after that, we have something called as activation, which is defined here as ReLU. ReLU is basically rectified linear units. All it does is any values from 0 to 0 and negative is just squashed to 0, and positive values are left as it is. And that's a nonlinear function. And right after that, we have one more dense layer with units as 10. So this means there are 10 neurons. And the activation for that layer is softmax. So what softmax does is basically it takes the raw values and it converts into probability values. So the third step is to configure the learning process using compile method. So we use model.compile. Here we specify the loss function, optimizers, and the metrics. In this case, the loss is something called as categorical cross entropy, which we generally use in classification. And optimizer here is SGD. You just pass it as a string. So SGD is a keyword here, and that's called stochastic gradient descent. Metrics, since we are doing classification, accuracy is the right metric. And next step is to train the model using fit method. So we use model.fit and then pass in the input training samples, which is xtrain, and its corresponding ground truth, which is ytrain. And epochs here refers to how many times the model looks at the entire training set. So if it means, if it's 5 here, it means that the model will look at the entire training set 5 times. And generally, when we train neural networks, we do it in batches and not just single images. So we just send 32 samples of input during one time step, and we update weights after each batch. So here the batch size is 32, and this can be set to any number, but you're mostly restricted by the computational bottleneck. So let's look at, earlier I talked about we have sequential and functional models. The sequential model is basically you linearly stack layers, and it's useful to build simpler blocks, simpler models with just a classification network and encoder-decoder models. One example of that is VGG16. So this is a standard architecture by Oxford Group. All this is doing is image classification. So it takes an input of 224 cross 224, is the size of the image, with 3 channel steps. It's RGB, and you feed it to a convolution network here. The black ones are basically convolution blocks, and the red ones are max pooling, and the blue ones are fully connected, and the last one is soft max. So it passes through this network, and at the end, it has 1,000 classes. So we have 1,000 nodes at the end to do the classification. Another example is encoder-decoder model. So this is also an stacked autoencoder. So what this does is it takes an image as input, and then it downsamples it to a very low resolution, and then it starts upsampling it back to the original resolution, and it reconstructs the image. This is commonly used in many applications, which I'll be talking about in future slides.
So this is in a way is unsupervised learning. So
yes.
You don't need labels.
We don't need labels. This is
good features.
Yes. Any questions so far? So the other class of models in Keras is called functional. So this is very useful if you want to build complex models like with multi inputs and multi outputs. And if you want to build complex models with, let's say you have a bunch of one model that's coming out, and then it forks out into multiple branches. I'll show some examples on that. And then if you have models with shared weights with multiple columns, you can use functional API to design such models. So we can see one example over here, which is doing action recognition. It's just a classification network. So there are 3 columns of CNNs here, and each of this column is receiving a video frame of an action, and all the weights are shared between the 3 networks. And there are a bunch of fully connected layers here, and the output features that comes out of these fully connected layers are concatenated and then passed into one more fully connected layer, FC8, and then classification is done at the end. So if you want to implement such networks, you'll have to use functional API in Keras, and this can't be done in sequential. The other application, so I'll describe one of the applications of functional APIs. So you can, there is a concept called domain adaptation in machine learning, where if you have 2 data sets called domain A and domain B, let's say you train your model with domain A, which are MNIST digits on the left, and you test the same model on domain B. The performance of this will be very poor. The reason for this is there is a huge domain shift between these 2, as in the model has never seen these examples during training. So once you test it with these, the performance drops because they are from different domains. So the solution for this is to adapt the model for both the domains, and this is an entire field in machine learning called domain adaptation. So here is one network. You can implement this network using functional API. So this is the one that I was talking about, where there is a bunch of feature extractor layers, and then it splits up into 2 forks. So right now this does domain adaptation. The way this does is you have a common feature extractor and you have a label predictor and a domain classifier. You feed both the images, domain A and domain B, through the feature extractor. And since domain A has labels and domain B doesn't have labels, only the images from domain A goes to the label predictor. And this label predictor basically does classification from 0 to 9. It's just a 10-way classification. However, the domain B, since it can't go here,
okay. Yeah. What's your name? Chris. Okay.
The domain classifier does binary classification.
20 minutes late. So it's not acceptable. Otherwise, I will ask you to leave the class. Next time, don't come late.
So the domain classifier is a binary classifier. All it does is it'll look at the image and say whether the given image is from domain A or domain B. So it's just a binary classifier. So how this is used in domain adaptation is as follows. So let's assume that we do backpropagation and gradient descent everywhere. So we feed in domain A and domain B. Domain A goes through this, does classification, and then domain A and B goes here, and then this is successfully it's successful in classifying domain A and domain B. But what we want is basically this label predictor to be good at classifying both domain A and domain B. So what we do here is we do gradient descent at this point, just like normal convolution networks. But at this point, we do gradient ascent here, but then gradient descent here. There is a gradient reversal layer at this point. So I'll give you the intuition about this. So let's say we are doing gradient descent everywhere. What this domain classifier does is, at the end of the training, it will be successful in classifying both domain A and domain B, and there is a clear boundary between these two. If that happens, then this classifier at the top will find it very hard to classify the domain B, because it has never seen these domain B samples, but it has seen only this, and it performs very bad on the domain B. But if we do gradient ascent at this point, what happens is now the domain classifier is finding it hard to classify the features that comes out of this. So you have a clear boundary if you do gradient descent at this point. If you do gradient ascent, you're trying to do the opposite of it. So this domain classifier is finding it really, really hard to classify whatever the feature that comes out of this. So at the end of the training, what happens is the feature values that you get out of this feature extractor for both domain A and domain B will be very similar, and the label predictor will be able to do a good job in classifying the digits. So such networks can be easily implemented in functional API.
So when you do the testing after training, you would remove that last point.
Yes,
right?
yeah. At test time, we remove this and we just use this because this right now is good at classifying both domains. So let's look at an example of how to implement a convolutional neural network using sequential model. So we can see a network here which takes a 4D input array and 4 convolution layers and 2 max pool layers and 2 fully connected layers. This is a mini VGG style architecture. VGG generally has about 16 or 19 layers. This has about 6. FC refers to fully connected, or it's the same as the dense layers. The input to this network is 4-dimension. This is in practice. So when we train any network, we train it in batches. So the end train here refers to the number of training samples. Height and width refers to the height and width of the image. And the channels refers to the RGB channels. If it's RGB, the value will be 3, and if it's grayscale, the value will be 1. So this is how code looks like in Keras. We import all the required packages, and we import all the required functions from Keras modules. And here we are just generating dummy data. This doesn't mean anything, but we just generating X train and Y train and X test and Y test. We use an NumPy random function. So the key here is that we need to set the data in the required number of dimensions. So since our model takes 4D input, so the first dimension here refers to the number of training samples. So that is 100. And then these two are the image width and height. And this is the number of channels, which is RGB. The same goes for the test. And test has only 20 images. And we set the corresponding ground truth. So this is the key here is that we need to set the data in the given required number of dimensions. It's the same network. So once we have imported all the required modules, we are using sequential modules. So we call the sequential class and assign it to an object. And then we start stacking layers. So the first layer is con 2D. It's a 2D convolution. And with 32 feature maps and 3x3 filters with activation as relu. And since this is the first layer, we have to mention the input shape. So we have designed our input. We have designed the data for having input as 100 x 100 and 3. So the input shape has to be mentioned here. And the second layer is con 2D again, same as here, and with 32 filters, and 3x3 is the size of each filter with activation as relu. And then we add one max pooling layer. Max pooling 2D is a 2D max pooling layer, and then we specify the pool size. I'll show you how max pooling works in the later slide. And then we have one dropout layer. So after that, we stack 2 more convolution layers. This dropout is optional. It's just a regularization trick. Using dropout helps in better learning process, and it avoids overfitting. So, but this is optional. So you stack 2 more layers of convolution, 64 with 64 feature maps, and 3x3 as the filter size with activations, and then same goes with the max pooling. And after this, so right now we are at this point. We have a layer called flatten. So what this does is the output of the convolution feature map. Feature maps will be 2D feature maps. Now, if we have to pass that to a dense layer, we just have to linearize the values in the feature map. So we just linearize the values of the feature map and then pass it to the.
Make a vector.
Yeah, we make a vector and then pass it to the yes.
Is there any mathematical difference between non-flattened one and flattened one?
No, there is no difference. It's just
since you have the fully connected, so you have to have the in 1D.
It's just changing dimensions. From cuboid, you just change it to a vector and then feed it to dense.
But in general, I mean, you lose the spatial information because you are taking all this putting there. So, because at the end we want just a classified, that which class it is, it doesn't matter. But some cases where we need a spatial information, we have to maintain an image
So we have a dense layer with 256 neurons and activation as relu, and then we have one more dense layer with 10 neurons, and then this is the last layer. So the activation is softmax, converts it to probability values, and then we start training it. So we set up the compiling process. We configure the SGD. SGD is basically stochastic gradient descent. This is the optimizer. We set the learning rate parameter. There are a few other parameters that comes with each optimizer, and we set up the compiling process with the loss and the optimizer, and then we use model.fit to start training the model, and model.evaluate to give a raw score for each of these. And if you specify metrics here, the output will give you the accuracy. In this case, since it's a classification problem, we get accuracy.
Question. First, can you define your own loss function, Keras?
Yes, you can do that. You just write a function with just like any other Python function, and then at this point here, instead of this string, instead of the categorical cross entropy, you just pass that function at this point. Loss equals the name of the function.
And the other question, if you want to have multiple loss functions at the same time, how do you do that?
You can start listing out the function, name of the function. Let's say you've written multiple functions, multiple loss functions, and then you put a square braces and then list out all the name of the loss functions that you have defined.
And what if one of the loss functions has different inputs, like not all of them have the same inputs, so the computational graph can automatically decide which input must use for each loss function?
Yeah, then you will have a different branches. So you will have different branches.
Exactly.
You cannot have the one as you explained to me, right?
Yeah.
Because you cannot have one branch.
One branch. So in that case, what you do is you can't do that with sequential way of writing the code. You'll have to do that with the functional way of writing the code. So in that case, I'll just go back to the previous slides. Sorry. It's in the next.
This one, isn't it?
It's in the next one. It's here actually. So in functional style of writing, you can specify what inputs match to what outputs. So you let's say you have 3 inputs and let's say multiple outputs. You specify input 1, input 2, input 3 in a square braces, and then outputs will be output 1, output 2, output 3. So it will match automatically depending on the position of your system.
So only one compiled function can work for all of them?
Yes, as long as you're training it simultaneously. So that's that. And let's look at how to train a simple neural network. MLP is multi-layer perceptron. It's just a bunch of fully connected layers using functional model. So similar to any other program, we just import all the required models. And for functional model, you have to import this class called model. So here, the way you write is slightly different from sequential. So you specify the input, this is a keyword here, and you specify the shape of it, shape of your input. And you assign it to a tensor. Next, you write your dense. Let's say we want to construct a network with just 3 dense layers. You write the dense layer, and you want to feed the input into the dense layer. So you specify it here. So this input passes through this dense layer, and then gives you an output. You take this output, and then pass it to the next layer here, and this passes through this dense layer, and then gives you another output. And you keep on doing the same thing for however long you want, depending on your architecture. So this X is again passed here and passed to this dense. So we decided to stop here, so we named it in a different variable, different name. So we call it predictions here. And these are basically 3 different dense layers with 64 neurons, and 10 neurons here. So once you define your graph, so this is the computational graph. Once you decide this, you need to explicitly specify what your inputs are and what your outputs are. So here inputs is inputs, which is coming from here, and then outputs, we want to tap the outputs at this point. You could even tap the outputs at this point by giving it just a different name. So we specify that here. And then just like sequential models, we use model.compile, specify optimizer, loss, and metrics, and then fit the data using model.fit. Yeah.
What is in the shape? What does 784 with the comma represent?
It's just a one-dimensional vector. That's the input size.
For example, sometimes for regularization, you need like coefficients of the layers. How can we take?
Oh, you mean L2 regularization or L1
X to load?
So each of these layers have built-in arguments to do that. Let's say if you want to specify L1 regularization, you have one more argument that's available in the documentation. If you look at that, you just specify L1 regularization there, and then you can specify parameters there itself. Yeah. So let's look at another class of neural networks, which is called recurrent neural networks.
Sorry, quick question. So far, everything seems very similar to TensorFlow.
Yeah.
In the long run, which is better to learn?
TensorFlow.
TensorFlow.
Then you can get a job in Google.
So let's look at another class of neural networks, which is called recurrent neural networks. So RNNs are mostly used on sequential data, like text, audio signals, or genome data. And they are basically of three types. One is the vanilla RNN, which is like the simplest recurrent network. And then there are modifications to that called LSTM and GRU. LSTM is long short-term memory networks, and GRU is gated recurrent units. So these two are basically designed to overcome some of the problems of vanilla RNN. An MLP, which is a multi-layer perceptron, which is just a bunch of fully connected layers, that and a convolution network, they're just feed-forward networks. You just pass data in one direction. But these recurrent networks have internal feedback. That's why they're used to model sequences. What this means is basically output at time t is dependent on the current input as well as the previous values. So here's an example of how an LSTM looks like. This LSTM over here is the same LSTM. It's not three different LSTM, it's the same LSTM, but unrolled through sequence. So let's say we are doing a task in NLP called sentiment classification, and we want to classify a given review. There's a movie review, and we want to classify whether it's a positive review or a negative review. It's just a simple binary classification. So to do this, let's say we have a review called best movie ever. Now, since LSTM is a mathematical model and it takes numbers as input, we have to convert these strings into numbers. So one way to do that is through embedding. There are different ways to embed. There's a whole line of research in NLP to decide what type of embedding is the best. And the simplest way to do that is one-hot encoding. So you feed that to the LSTM, which will, so the output of embed layer would be a real valued vector of some size.
So the one-hot encoding, I think the people who don't know, it's a very simple thing. So if you have total vocabulary, say 3,000 words in the English language, this is an example. So you will encode each word in 3,000 dimensional vector, and each of the word will have one of the position in that vector. So the best will have 50th position. So 50th position in the vector will be 1, rest of it is 0. Maybe movie will have 100th position, 1, that's called one-hot vector, very simple thing. So what you're doing, you're mapping words into a vector. And there are different, other better embedding, which is called word-to-vec, which you can learn, which are more efficient, but this is an example
simple
of this embedding.
Okay, so let's look at how to build a recurrent network in Keras. So here's the network, which is similar to the previous one, where you want to do sentiment classification. And we just import all the necessary libraries and the necessary layers. So we are building a sequential network here. So we import sequential and then assign it to an object. And then the first layer is the embedding layer. As we can see here, we pass in the data and we have the embedding layer here. So this, the output of the embedding layer has to be decided. In this case, it's 256. It's just a 256 dimension vector. And the input to that, and next layer is the LSTM. So LSTM, the 128 value that we see here is the size of the output vector of the LSTM. So the output, so LSTM takes an input and then it spits out an output. So the output dimension has to be specified. So it's a 128 dimensional vector. you can specify this to any number, and this will change the performance of your network. And right after that, we have dense layer. Since it's just a binary classification, we just have one neuron, and activation is sigmoid, which just converts value from 0 to 1. And then we compile it just like any other, just like how we do it for CNN. We use loss functions, optimizers, and metrics. We also use, we train it with model.fit by giving X-train and Y-train, specify batch size, epochs, and then evaluate it. So there are several types of convolution layers. Yeah.
Can you please go back? So here the Y test, the labels that you are giving, are those one-hot vectors, or?
No, Y here is just positive or negative at this point.
I'm sorry, the X-train.
X-train and Y-train.
Yeah, X-train would be one hot.
Yeah.
That's like the simplest way to do it.
Okay, then if you're using that as one hot, then why do we need the embed?
So one hot vector is like a naive way to do it. So here embedding layer has weights that it can learn during training. So if you pass in one hot encoding through the embed layer, the output will be a real valued vector of 256 dimension. So it will be a real valued vector.
So in this thing, in a way, the sample is a sentence, right?
Yeah.
And then output is yes or no, positive or negative.
Correct.
So X will be one sentence, movie sentence, movie. Then Y will be corresponding to that positive.
Label, yes.
Then will be another sentence, positive, negative.
Correct.
So that's like that.
Yeah. Any questions so far?
So the shape of X-train here would be then the number of?
It would be a three-dimensional matrix. One is the batch size. The other one would be so it's like a matrix of, let's say if you have 5 words in a sentence, each word will have a one hot encoding. So you assign it along the columns. So one hot encoding, first word, second word, third word, the fourth word, and fifth word. So it's like a matrix of one hot vectors, and then you feed that as the.
Then what if you have inputs of different length? I mean, if you have words, I mean,
yeah, correct. So in that case, you just generally do zero padding. You check the training set, and you look for the biggest sentence, and then you make sure that all sentences just get zero padded to that length. That's like a naive way to do it, but I guess there are dynamic ways to do it with other frameworks.
The important thing, the LSTM will take any length sequence.
Right, theoretically, yes.
It doesn't have to be fixed.
In embedding, what's the next features?
It's just the size of the time steps that you want to pass it next. So max features would be, if it's let's say 5, the LSTM will eventually roll for 5 steps. So the LSTM will automatically infer the shape from the embedding layer, and then it will roll 5 steps because it will know that there are 5 words to look at.
So LSTM is input, and then it will do output. Input and output. Now it will do output even there's no input. You can have same input. So basically, how many times you want to run. Of course, it will depend that if the length is at least 5 sentences, you want to go through the whole sentence, you know? But you can do 100 times also. So which is fine. So
there are different convolution layers. 1D convolution, which is mainly used in audio signal processing and natural language processing. It comes with various arguments. This is where I mentioned where you can set the regularizers, L2 regularization, L1 regularization. By default, it will be none. You can just specify a keyword here. And the main things are the number of filters that you have to specify, the kernel size, and strides, and if you want to zero pad your feature maps, and the activation is something that's important. And also the kernel initializer, which is the weight initializer, where you set the initialize the number of initialize the weights, values of the weights before you train the network. So that's specified here. Similarly for 2D convolution, which is mainly used for images, And 3D convolution, it does convolution along the third dimension. So it's used in videos to analyze videos. I've been mentioning about pooling layers all this while in some of the networks. So there are different types of pooling. One is called max pooling, and the syntax is as follows. You have to specify the pool size, which is important. So all that max pooling does is, since it's a 2x2 window, assume that this matrix is an image, and you have a 2x2 window here, 2 pixels, 2 pixels. It'll take the maximum out of these 4 values and then gives us the output. So in this case it's 6, and then here the stride is 2. So instead of going to the next cell, it'll just skip that cell and go to the next one. So it'll take the maximum in this green section and gives you the maximum value as the output, and similarly in the x and y directions. So in this case it's 3, in this case it's 4. This is max pooling. Basically you reduce the dimension of the feature maps or your image. Average pooling is similar. Instead of taking maximum, you take average of these values and you just output that. Upsampling is sort of like the reverse of max pool, but in this case what you do is you just repeat assume that this is a pixel value, and then you just repeat it some number of times. That depends on the size that you give here. So if it's 2x2, then this is repeated 2x2 times, and the same goes for all values. This is upsampling the size of the feature maps.
But in this one you can also use the convolution.
Yes, you can use deconvolution, which is so. Just know that none of these have parameters to learn. They're just straightforward operations, linear operations. None of these have any parameters to learn. There are a few general layers like the dense layer, even that comes up with a lot of arguments, and you have to specify the number of units, and activations are the main ones. And then dropout. So dropout is assume 2 fully connected layers, and there are connections between these 2. Now if we apply a dropout between these 2, and we have to select a rate. Rate is basically a value from 0 to 1. If you put, let's say 0.5, just 50%. The connection between, randomly 50% of these connections will be dropped during training, and the rest 50 will be connected, and this happens in a random fashion. They do this to avoid overfitting, and there is
what's noise shape?
Noise shape. The connections that are dropped are done randomly. So how do you select the random connections that you want to drop?
With distribution?
So that distribution is specified there.
And you can do uniform or
Gaussian distribution. The other one is embedding layer that I earlier discussed. So there are several optimizers available in Keras. So optimizers are optimization basically is finding the best set of parameters for the model that gives you the lowest loss. And you find that using different optimizers. There are several optimizers available depending on speed of convergence, and they vary based on speed of convergence and our ability to get stuck in our local minima. So the most popular one is stochastic gradient descent, SGD, and then there are variants of it, SGD with momentum, ADAM, ADAGRAD, RMS prop, ADA delta. Each of these have their own merits and demerits. If you want to understand the mathematical idea behind each of those and the differences, I would suggest that you can look into the deep learning book, and here's the URL.
I suggest everybody to get this book. It's free. It's a very nice book from Ian Goodfellow, the guy who invented K. So you should get it.
Yeah.
Are all those optimizers built into Keras?
Yes, they're all available in Keras. You just call the name and you can start using it. There are several loss functions available in Keras. The popular one is mean square error. So you have a predicted value and you have the ground truth. You compute the difference between them, square the error, and take the average over the samples. That's MSE, and it's similar to mean absolute error. Instead, here you don't square it, you just take the absolute value of the error. These are generally used in regression problems, and there's something called as categorical cross entropy, where if you are doing classification on k number of classes, you use cross entropy there. And there's something called a scale divergence. If you have two probability distributions and you want to see how different these two distributions are, you use scale divergence to compute the difference value.
Sure. So how many people know what is entropy? Entropy, everybody knows? So entropy is the P log P, right? Probability and log of probability, entropy. Now, what is the cross entropy? So it is it's a cross between two distributions, and that's what you see there, the y of ik upstairs, and then we have another term will be the log of p of y. So that is the difference, that you take a p from one and log of probability of another distribution, and that gives you how similar these two distributions are, and that is a very widely used error for the classification, and it is derived from the KL divergence. So KL divergence, in the bottom line, it's saying we have two probability distribution P and Q, and we want to find the distance between them. And that distance is log of P minus log of Q, and expectation over that, mean over that. But this expectation we are going to take from the probability distribution P, not Q. So they are not symmetric. And so you can actually, from here you can go to the cross entropy, because that's where you get the idea. So when you do the classification, you want to say that in each sample you want to classify it, and there are many samples. So you want to come up with classifier such that the distribution of the output or classification is very similar to distribution of your ground truth. And that's where the whole idea comes in. And we are going to talk about that more, but you need to understand that.
So in Keras, once you're done training your model, you want to save your model, you want to save your weights. Now there are ways to do that. So to save models, you just have a method called save. So once you have the trained model, which is stored in this object, you just use model.save, and then you specify the path or just the name of the file that you want to save. And this saves in a HDFI format. And you can delete the model using DEL. And if you want to load the model, you import this function and then use load model and name of the model that you have saved. So the saved file contains three things. One is the architecture of the model, and the weights and the biases, as well as the state of the optimizer. And then you can use, if you don't want to save the entire model, and if you want to just save the weights, you can use save_weights and specify the name. And similar goes with the loading weights. There's another argument here called by name. So let's say you have a trained model, and you want to use it in another complex model that you want to build upon that. So you add few more layers which are untrained, but you want to sort of get the weights of the trained model to the existing base architecture. If you want to do that, then you make sure that while you're training your base model, you specify the name for each of the layers and save the weights. And once you load the weights, if you give by name true, it will automatically shift all the weights from this weight file to those corresponding layers. You don't have to individually specify. So the other uses are if you want to extract features from pre-trained models. So let's say there are several pre-trained models which are trained on huge data sets. There are VGG, ResNet, and Keras has about six or seven pre-trained models. And if you want to use them, you just import the network. For example, in this case, it's VGG16. You import the network and you specify the weights. So this network has already been trained on ImageNet, and the weights are saved in your computer. So you just specify that you want to transfer the weights that are trained on ImageNet, and then include top is basically the last layer, which is the classification layer. If you say include top is true, the last layer will be included, which consists of 1,000 neurons for classification, which for ImageNet. If you want to exclude that, just type in false, and then the last layer will be excluded. So to test on single image, you import the image and do a bit of pre-processing. So each of these networks are trained with certain pre-processing done earlier before the training. So you want to make sure that at testing time you do the same pre-processing and then feed it to the model. So you use model.predict and pass the image to get the features of the penultimate layer.
Can we go through those segments, the size, target size, and
yeah. So this is the assume that you already have an image called elephant.jpg, and you want to make it an array now. So img is image.loadImage, and you specify the path and then the target size. So this will basically Keras has some built-in pre-processing functions here. So if you import any image and you specify it through this, it will resize it to 224 cross 224, because ImageNet, the dataset called ImageNet, the images present in that, they're all of 224 cross 224 size. And you pass that to the IMG. Here you convert it to an NumPy array. And expand dimensions is basically, since this will be a 3-dimensional array, you want to all our models takes 4-dimension input, so we expand one more axis called 0, and we are just passing in one image, so batch is just 1. And pre-process input, this has some built-in functions inside Keras. You can look at the documentation. So this makes sure that it does mean subtraction between, it does channel subtraction and computes the standard deviation. It's just pre-processing that is required to send it to the VGG. This is done because the VGG, when they trained VGG, they had done all this pre-processing, and you want to make sure that the testing conditions are also similar. And then you pass it through model.predict to get the features. So I'll just give a brief introduction to the popular deep learning architectures. The popular convolution networks are AlexNet, VGG, ResNet, DenseNet, and generative models are autoencoders and generative adversarial networks. So popular image recognition networks, which are CNNs, are AlexNet, which was introduced in 2012. This was the year when, this was the architecture and the year when the whole deep learning revolution started. It's by Alex Krzyzewski and Jeff Hinton. And then in 2014, Oxford group came up with this VGGNet. So this is about 8 or 9 layers deep, but then VGGNet was introduced in 2014, and that was 16 and 19 layers deep. In 2015, Microsoft came up with this ResNet, which was in different versions, like 18 layer, 34 layer, 152 layers, and there was one with 1,000 layers. So the key difference between the earlier architectures and the ResNet is that they have introduced something called as skip connections, residual connections. So the output at this point of this layer is just bypassed to the point at this point. It's just bypassing across few layers. So when they designed this VGG, they tried to design VGG network with 20 plus layers. When they did that, they realized that they didn't gain any performance by going further deep. They realized that they have a problem called vanishing gradients, where you compute gradients at the end, and then by the time it reaches these layers, the gradient value will be so low that if the weight updates is not significant. So there was absolutely no training happening at these points when it was deep. This problem was sort of overcome using ResNet, and this trick of having residual connections enabled them to expand this to 1,000 layers.
So with those connections, though, do they just randomly choose which input is going to go? Because there's input going from just the normal convolutional layer, for example, from the second to the third convolutional layer, but there's also one going from the first to the third. So do they just randomly choose which one to process?
No, this is designed in a symmetric fashion where you have this. So they just, after the first layer, which is here, they just add skip connections after every two layers. So there is a symmetric pattern that's followed throughout the entire network. And in 2017, they came up with
It's maybe a bit irrelevant, but how can you see the output of intermediate layer in Keras? Because we have a deep network, and the compile function is the point that we built the whole network. So how can you see the value of intermediate layers if you want to check something?
you can do that using functional API, where there is another method called getLayer that's there in the documentation. So you specify the place where you want to tap out the input, and you specify getLayer at that point. You will get the you can tap out the input.
We should call that after compile or before that?
It's during the training itself. You'll have, so when you design the entire graph, you just specify getLayer at which point you want, and then you will see that when you do model.predict or model.evaluate. When you do model.predict, it'll return two outputs. Let's say you have a classification network, it generally returns one output, but then you specify getLayer at some point, and when you do model.predict, it'll return two outputs. One is the final output, the other one is that intermediate. In 2017, they came up with DenseNet, which is similar to ResNet, but then there are dense connections between each layer. As you can see, each circle over here is like a CNN block, and there is dense connections.
So this is what you asked now. In this one, everyone is connected. The other one was just two, only this.
Well, my question was more like because since there's two connections coming in, which inputs are chosen?
Oh, both are. So at this point, they both are added. So the value that comes, yeah, element-wise adding, addition. So there is a important challenge in computer vision called ImageNet, where you have 1,000 classes and more than 1 million images in the training set, and this has been there for years. So people back in 2010 and 2011 were using deformable part models and a few other shallow networks with hand-engineered features, and they used to get an error rate of 25.8%. This is the error rates. And in 2012, AlexNet, I mean, there's a huge margin in error in 2012, and this won the competition with 16.4. And then in 2013, there was a network called ZFNet or something that came up with a lower error. And then in 14, VGG, and then GoogleNet and ResNet, and then we have even lower errors now. So this is one of the, so let's look at autoencoders. This is one of the generative models. So the basic idea is that you feed in input images and you generate back the same input images, and you keep doing this for the entire training set. But the dimension of the images keeps getting reduced, and then it gets upsampled again. Where is this used? There is something called as unsupervised representation learning. Like, people don't want to label each and every image out there because it's expensive and time consuming. So people are looking into how to find unsupervised representation. So they use autoencoders to do that. The other use is to reduce the dimension of the input vector. And the other application is denoising, where you feed this as input and then you get this as the output during training. And then at testing, you just feed this and you get the denoised version of it. The other one is generative adversarial networks, which is very common right now. So there are two CNNs called generator and the discriminator. They both are convolution neural networks. This generates an image from a random vector. Initially, it will be just an image that human can understand. But then you feed that to a discriminator, which is again a CNN. And you have real world images which are taken from cameras, and you feed that to the discriminator as well. So the job of the discriminator is to discriminate the images, like distinguish the images as the real and fake. This is the fake because it's a generated one, and this is the real one. So the discriminator and the generator plays a game where this tries to, the generator tries to fool the discriminator, and the discriminator is trying to do a good job at discriminating both these two. So at the end of the training, the generator will be really good at generating real world images, like the images that are very close to real world images, and the discriminator will reach an equilibrium. So there are very interesting applications of GANs. So they use textual descriptions to generate images. So as you can see here that you give this description to the network and it generates the images.
So again, in this insert text, as we did for the movie, so we'll do the same thing. We take each word and do the one-hot encoding, just keep pairing these vectors. And that's it.
So the input to the network is just this at test time. We just describe the image that we want to generate, and then it starts generating such images.
And these are all generated by?
Yeah,
this is all generated by GAN.
Wow.
And they're generated from a noise in the text.
And we can do we can perform arithmetic in latent space. So if you have images with man with the glasses, and then if you subtract man without the glasses, and then if you add woman without glasses, you get woman with the glasses. This happens in the latent space. It's latent space arithmetic. Other interesting applications are you can generate images of the same scene with different weather conditions. Here it's winter, and if this is your input, and then it can generate the same image with summer theme. And here it's sunny, it's rainy here, it's the same scene. And you can transfer style of painting from one to other, and you can even change the content. In this case, the same scene with zebras is changed to a horse, and the paintings are a photograph is painted with different artists' styles.
So this is one of the paper, it's on our list. So if anybody wants to do that, present that, you can select.
It's called Cycle GAN. Apart from the networks that you see in the documentation, there are few contributed layers since it's open source. There are few contributed layers that you can check out in the GitHub link. Those are not completely verified, so that's not made it to the documentation yet. So there is Keras documentation here, and then Keras blog, where Frank Escolet himself writes very interesting articles. Questions? I'm sorry?
What about reinforcement learning? I guess implement that to
Keras doesn't directly have packages that support reinforcement learning yet, but reinforcement learning, deep learning is just a small section in reinforcement learning. You just learn, let's say if you're learning a queue function, you just use a convolution network to do that. You can do that using Keras. But then there is, if you want to set up the reward function, all that is just direct Python, or you could use other Python-based libraries. Any other questions?